Hi folks. Alright, today we're going to be talking about PipelineC, and it's in the context of buying your first FPGA development board. And this link you see down here at the bottom, dev board setup, is where all this is going to be coming from, so any links you're looking to have will be found there. Okay. Outline for today. We're going to be talking about things to know before you go and buy your first FPGA, going and getting your files and your tools all together. Talk about the top level of the design, your inputs and outputs, what clocks you're going to use. Also going to be talking about simulating your design, running synthesis, place and route, making sure you meet timing, and then a large majority of this talk is some examples, the big one being UART, receive and transmit loopback. Alrighty, before you buy your first FPGA, some things to know. FPGAs are hard enough, so if you're going out and you're finding some old piece of hardware, you're probably going to be using some old tool. If you find some big expensive piece of hardware, you're probably going to need some big expensive tool. You critically need to have a list of the FPGA pins and how they connect to the board that you're using. That's typically in the form of constraint files, XDC for Xilinx design constraints, and PCF files, pin constraint files for the pico-ice flow we're going to be talking about. And you want to be sure that it comes with some kind of power on test or blinking demo you can compile and make sure everything's working. More examples the better. As I mentioned, we're going to be using two dev boards in this talk here. The first one being the pico-ice from tinyvision.ai, which they very nicely shipped me one of their boards to work with, and it's been excellent. Other board I'm going to be talking about is the Digilink Arty. It has a Xilinx 700T FPGA on there. It uses the Vivado proprietary tool. But most of this talk is going to be using that OSS CAD Suite, open source software suite, and that has a makefile driven flow where you just need to set some environment variables and you're off and running. Okay, just giving an overview of what we're talking about here. This flow should be familiar to other FPGA build flows if you've ever encountered them. Starting at the top row here, for the pico-ice, things are orchestrated by a makefile, which invokes GHDL, UOSS, and NextPNR. For the RD flow, you get to use the Vivado tool and those projects. As mentioned, you definitely need the constraints file that comes with your board. So pico-ice comes with a PCF file, and the RD comes with an XDC file. This flow has a wrapper of standard system Verilog or VHDL that sits around the PipelineC design, and that's for things that are just generally more complicated to try to insert into PipelineC than just put in a top level wrapper, like tri-state things and complicated fancy I/O for your FPGA. The input file to PipelineC is a header and a top.c file, and from that you get VHDL in the form of a list of VHDL files or a tickle script for using Vivado. When working with top-level IOs in PipelineC, you'll see code like this typically. This first bit here declares an input called myInput, it's a single bit. It declares an output called myOutput, it's also a single bit. And if you run the PipelineC tool specifying a top called myTop, you end up with VHDL that looks like this, a myTop entity, and my input and my output, input and output ports. I had mentioned that PipelineC design typically sits inside of some wrapper where you'll have things like tri-state buffers if you need them, and then that's actually the top level design of the FPGA, and your FPGA is sitting on your dev board. So when you write code like this, starting up here at the top, you're specifying a function that's going to be at the top level, so it can drive top level I/O, and it has a operating frequency of 12 megahertz. So output of the tool is going to produce VHDL by default that has the clock rate in the name of the clock port. If you want to override that, there's some similar looking syntax to last slide where we declare an input. We're going to call it PLL clock this time, and another macro to say that that PLL clock has a frequency of 12 megahertz. And now your top level VHDL just has a PLL clock input as opposed to being named with the clock rate. Getting into some examples here, I could talk about the kind of most simple thing you'd be able to do. Have a register that's incrementing and counting. So let's walk through this design here. At the top, we're including some headers for arbitrary precision types and this debug port we're going to use. Below, we're telling PipelineC about the FPGA part we're going to use, because PipelineC can also run synthesis and place and route in the background for you. Finally, we're actually using the debug header to declare a debug output here, it's counter debug. And next we get into the body of the module here. It's calling it main. It's going to be operating at 25 megahertz. We have a counter here, 32 bits, and critically static, meaning that's going to be a register. It's maintaining state. Next line here, we connect the debug port we declared, and then we got a fun printf here, which works in simulation, as you'll see. And we do our incrementing of the counter and connection to the output port. And on the left here is the schematic which represents that. Critically, your counter register going through an adder. It's also making its way to the output port, and then this debug signal kind of pops out of the top here. PipelineC can help you simulate this design. So if you look at this command line that's down here, we point PipelineC at the counter file, and we tell it to simulate using GHDL and CocoaDB. So you might get some output like this, a waveform file that you can use in your favorite waveform viewer of choice, like Surfer here. There are also some outputs printed to the screen. The printf from before shows up, and the debug signals are printed in all the situations here. And yeah, this is going to work with all your VHDL simulators of choice. And finally, again, using the OSS CAD Suite, we can add on a conversion to Verilog with GHDL and UART and use that to run Verilator as well. PipelineC can also run synthesis and place and route. And background here, synthesis is what is converting your description of the hardware into actual FPGA elements you're going to use. And place and route finds positions for these elements in the FPGA and makes sure they can be connected together. As mentioned, PipelineC can run this in the background, and you'll see outputs like this from the tool. UART is giving you counts of flip-flops and LUTs. XPNR giving you counts of logic cells, and Lovato does something similar and tell you about your flops and LUTs and carry chains. I mentioned on the last slide how place and route is finding positions for all the FPGA elements and making sure they can be connected together. Part of solving that problem is making sure as signals propagate across the FPGA from your flip-flops through your LUTs off to other flip-flops, that upon meeting the clock edge, that data has been stable enough to be sampled. It's called meeting timing, and if you end up doing a lot of logic in a single clock cycle, that makes it harder to do. So from a tool like XPNR, you'll get errors like this if you don't meet timing. You wanted to meet this target megahertz, but you actually only made it to some lower value, and it'll print out for you a full dump of the path from source flip-flop at a positive edge to another destination flip-flop at another edge. Lovato does something very similar. It'll give you some red text here telling you failed, a warning telling you failed, and another a printout of from the source to destination and what it went through in between. So PipelineC, as mentioned, can run synthesis and place and route in the background for you, and it's doing this for two reasons. The first being to pipeline things. As you might have guessed by the name of PipelineC, it can automatically pipeline things for you. So in a situation like, oh, I've stuffed my addition and my multiply into one cycle, PipelineC can break that up into 2 cycles and give you a higher operating frequency. You can disable this through various command line arguments, and again, it's this pragma that you've seen in the code once or twice now that's informing PipelineC about the FPGA part, and so it knows what synthesis tool to use, and it can also just provide that timing feedback for you a little nicer than either NextPNR or Bravado can do, hopefully. And so you might see a message like this from the tool if it runs into something it can't automatically pipeline for you. Okay, we're getting into the next section here, which is going to be a lot of example code. So take a moment, take a breather here, and all of this code, again, is at this link here, this dev board setup. It's the jumping off point for everything you'll see, so just visit there and you'll be able to find all this examples you're about to see. Alright. First example everyone wants to see is blinking an LED. So let's talk about what you're going to see as relating to the top level here. Along the left, some similar declarations of some outputs. On the ICE40 FPGA, the pin constraint file just names things ICE, and then the pin number shows them to do the same. But eventually, you map certain pins to their functionality, like so. And then you can write code that looks like this. You'll include your header over here, and we can start defining things for a counter, width of the counter, and again, static is the register. It's your counter. What do? You increment it every cycle, and in this case, our active low LED bits here are just connected to the blue LED. When you go and run the PipelineC tool, you'll get an output VHDL module that looks like so. That is if you ran with PipelineC top. And by default, you'll see that clock port with the rate, and then the other output ports as declared. And that very easily just wraps right up into this wrapper module that actually is the top level for your FPGA sitting on your board. You know, if your design is always going to be as simple as this blinking LED, you probably don't need this wrapper. Again, wrappers for stuff, weird stuff like tri-state and special I/O you might need. Okay. The rest of getting to the top level of the FPGA here, the constraint files. For the pico-ice, you have the PCF file. Again, similar to before, telling our pins like ICE39 is pin 39. That's great. Showing here also the constraints file for the ARTI. Just so you have seen that before. Very similar looking things, telling what pins relate to what name ports, and includes defining the clock here as well. Finally, pushing this through the very nice makefile based pico-ice build flow that comes with the example. I've added in a bit to invoke PipelineC as well. So you set environment variables like the path to PipelineC and the path to your OSS CAD Suite, and then you can just simply make clean all and build the entire thing, which will, as shown here, first invoke PipelineC on some top file. You're telling it where to put your outputs. UART comes in invoking GHDL2 and looks at the output VHDL files. It produces a JSON file, also using that wrapper around the PipelineC VHDL. And finally here we're invoking NextPNR, which takes in the JSON file from UART and your pin constraints file, mapping all your I/O to FPGA pins, and then it produces an ASC file output that hopefully has met timing to meet a certain clock frequency. Last fun bit here about blinking LEDs. Okay, what if it doesn't meet timing? As written, it would be pretty hard to not have that blinking LED meet timing, but if you change it a bit, and for instance start counting in floating point instead, so here we've changed our type to float, now we're doing a plus 1.0, so that's a full FP32 add, and then to actually get the binary to flip our LED bits, we casted it back to an integer there.
This is much more expensive than doing an integer add, and so you'll see things like this from XP&R. Here's your report from your clock edge to clock edge. You have many nanoseconds of logic and routing in between, so you're not going to meet even your 25 megahertz goal at best. Maybe you could do about 10 megahertz. It's pretty slow. Alright, so we're getting into the bulk of the talk here, which is a UART loopback. And initially we're going to start off with a trivial case, which is just taking the input receive wire and connecting that to the output transmit wire. In the default Raspberry Pi firmware that comes with the pico-ice, you get this TTY device that'll pop up on your system, and if you type into the terminal with this loopback in place, you should see your characters printed as you type them, which is evidence that you have your basic setup working. Part of which is making sure you had your pins correct. This default UART is pin 25 and 27 on the pico-ice, so it gets set up like so. You specify some inputs and outputs, and which is the transmit and receive, and what clock rate you're running at. And in the PCF file, you have more constraints that say similar things. Okay, for receiving UART, the protocol is byte based, so there are 8 bits you're intending to pull off the wire and assemble into a byte and do something with. And so in this design, we're going to receive UART by first putting the input wire into some module that produces a stream of bits that is 8 single bits. And then we're going to have another module here that takes those 8 single bits and produces 1 single byte. This is where we also introduce the concept of a stream. In PipelineC, this means it's some data signal, but also has a valid bit. So if you've done FPGA design before, you might be familiar with things like valid bits, and in PipelineC, you could imagine a struct that has some data and a single valid bit. That is actually what gets wrapped up for you in this stream.h header. And so if you see something like stream of data type, that's exactly what we're applying. It's a struct that has a data field and a valid. And so that's actually the type that is the signal moving between here. So there will be 8 valid pulses coming out of this first module, and a single valid pulse coming out of this module, and that's the 8 input bits and the single byte output bit. Okay. First part of that we're going to be focusing on is that module that takes the input wire and outputs the stream of 8 bits, and it is a state machine. So we're going to define a enumeration for the state machine states, and the signature for this function here, right? We have our input of the UART wire, and our output of the function is a stream of bits. And showing here, we're going to be filling in the state machine part of this, which starts off with having a register for the state. Okay, so what does the state machine for receiving UART look like? We're going to start off in our idle state, and while we're in this idle state, we are waiting to see the input wire go high per UART protocol, and once we see that, we begin waiting for the start bit. As we transition to the waiting for the start bit, we reset a counter as well. Then, while we're waiting for the start bit, we are waiting for the input wire to be the start value, which is low. So once we meet that condition, we start counting along. So where are we? We're over here where we've just met the start bit coming in, and we start counting, and we're going to count until we get halfway through a bit period. That's clocks per bit divided by 2. Once we're halfway through there, we go to our next state of receive, and we reset some counters as we do so. In this receive state, it's good to know that by default from our state machine here, we're not outputting any bit, and you'll see down here later where we do output a bit. So in the receive state, we're counting along
and we're going to count a full bit period. So we're counting from the middle here, a full bit period, count, until we're in the middle of the first data bit here. We're going to reset the counter because we're going to be doing that again for other bits, and then we're going to take the value off the wire, we're going to sample it, and then we're going to signal that that is valid this cycle with a valid. Increment some other counters, and that's what's going to let us do this 7 more times, where we count, sample, count, sample, each time sampling in the middle of the bit period, until finally we go back to idle. The stop bit high is also handled by the idle state. So in the last slide we saw the state machine for decoding the UART protocol off the wire and outputting our 8 sampled bits with our 8 valid pulses. The next bit in the chain here is the deserializer, which is going to take those 8 single bits and output 1 byte. So what do we have here? Input is the bit stream, your single bit of data, and it's valid. Output from this module is a byte stream, so 8 bits and a valid. Luckily this deserializer can be declared with a helper header here from stream deserializer.h, and this is the code that you get from that helper macro. Okay, bringing it all together here for a UART media access controller, you might say, a MAC, as things get called here. Again, we're talking about this chain of the input wire here, shown in green, going into the UART RX 1-bit module here first. Out of that is a bit stream. That bit stream is input to the deserializer. The deserializer output is a byte stream. And now, if you've been reading closely, there are some ready bits in here and mention of overflow. So what happens if, as your bytes are popping out of the deserializer here, you're not ready for them? This would be an overflow situation. UART has some flow control bits, if I recall the protocol, but we're not using them here. So what's going to happen is this module is going to output this byte, and if you're not ready, the byte just falls on the floor, and we have this overflow logic that if we're outputting a valid byte and the receiver's not ready to get that byte, we signal overflow. That goes nicely into the interface we're going to show users for this. This is a valid and ready handshake. That is, we have valid and data stream parts that we're outputting, that we were receiving, and then as an input to the receiver is a ready signal. And there's some good tutorials online about valid ready handshaking. Critically, in the name, when the condition is valid and ready, that's when the data transfer happens. So that way you can have flow control over your path. And in this case, as said on the RX side, if we're not ready, we'll just see the overflow happen. So we just finished talking about the receive path and its valid ready handshake that the user sees. On the transmit side, this is the ready signal is going to be even more important, because it's sort of reverse of the receive. We have a serializer instead of a deserializer, which comes first instead of the state machine transmit protocol portion. And the ready flow control is important because, for instance, while your transmit module is putting out the protocol onto the wire, transmitting your bit, it has to be signaling, no, I'm not ready for any more bits coming in. It's currently sending bit. And that propagates back through, and you eventually get I'm not ready for more bytes to transmit into the Mac. So we're going to be breaking this down. This first image is the easier way I tend to write things. It doesn't show the ready signal coming back. It's implied, but it is there. It's going the reverse direction of the data signals. And reverse of the receive side, we're going to have one valid pulse in of the byte we want to transmit. Out of the serializer is going to come 8 pulses of the single bits that we're wanting to transmit, and they're going to be coming out as signaled ready by that module. As mentioned, it's going to be slow because it's putting it out per the UART protocol. And yeah, again, you're going to see code with these stream helpers, and let's get into it. So, as mentioned, reverse of the receive, we start off with the serializer instead of deserializer. We're putting in 1 byte, and we're getting out 8 bits. We can look at the signature of the module here. Its inputs are the byte in that we want, and the ready signal for the output bit stream. The output of this module is the bit stream and the ready signal going back saying if it was ready for that byte you're trying to input. Again, this all is included for you in a helper header here, stream serializer.h, and this macro declares exactly this code above here. After the serializer producing the stream of 8 bits is the state machine for putting those bits onto the wire. And again, there's an enumeration for the states that we're going to use. The inputs to this module is the bit stream, and outputs from this module are the UART transmit wire and the ready signal for if we were ready for that bit coming in. The first part of the state machine here we're going to see is declared the output signals as this O variable, and they're all default zeros, all these variables. So critically, we're signaling not ready most of the time until eventually we're going to signal ready for when we are ready for that bit we'll get to. So in the first state here, idle, we're waiting to see the first bit from the serializer show up. It's saying, a byte is being serialized and we have the first bit ready. Let's start transmitting. During that time, we're putting the UART idle signal out on the wire, and like mentioned, we're waiting to see that first bit show up. We have not signaled ready yet. We're not taking that bit yet. We just saw it show up, and we're going to start transmitting, which is starts with the start bit. So we get into sending the start bit state. While we're in this state, we're putting on the wire the start bit value, and we count along, count. We count a whole UART bit period as we send the start bit, and then we transition into transmitting the data bits. Critically here in the transmit state, this is where we're actually taking the stream of bits that are coming in, and we're using their value to drive the output wire for a whole UART bit period. And as we do that, we're signaling ready and pulling off all 8 bits from the serializer that's feeding this module. So okay, we're in this state, and what we're doing is putting on the output wire is the bit stream data, and we're counting along for a whole UART bit period here. And then once we've reached the end, we've counted off the whole period, we signal ready. So we took that bit and we used it. And we reset some counters because we're going to be doing this again for all 8 bits. So again, we count, and once we've transmitted that bit, we signal ready again, gets the next bit ready for the next cycle. We count, and transmit. We do that 8 times, and then finally we go to sending the stop bit, which I'm not going to show because that looks a lot like sending the start bit. And from there back to the start for the next byte to transmit. Okay, bringing the transmit side all together here for another media access controller MAC thing as described here. It's the reverse of receive. Again, the serializer's first, followed by the transmit state machine. And critically, what I want to highlight here is in green, bright green, it's this feedback. So this is the first time we have to deal with a signal that's going the opposite direction of the data flow inside of a module here. And to do that, you need this pragma feedback. And so essentially you are behaving as if you have the value before you've actually assigned it.
give this pragma, and you'll notice the serializer here has an input, which is the ready signal. We're going to use it, but it's not later until the output of the transmit state machine is actually available, and we drive that ready signal later here. But with the pragma feedback, you actually get this bit of hardware highlighted in green. And again, if you read closely here, this module doesn't have any listed inputs or outputs, and that's because we're using an interface that exposes global variables. And again, it's this valid and ready handshake. Data isn't transferred unless we're valid and ready. This time we're over here, direction-wise. We have an output, which is the ready signal. Am I ready to accept this byte to transmit? And I have an input stream, which is the byte we want to transmit. Okay, so finally we're going to be pulling together the receive side MAC and the transmit side MAC, and we're actually going to do a byte level loopback now. So, okay, you have your PC with your single UART transmit into the receive side of your FPGA, and you have your FPGA's transmit output going into your PC, and you'll write some code like this where you have your I/O and a top level header. We've put the MAC code into its own file there, and you can write this here where, what are we looking at? The input of the transmit side is the output of the receive side, so that's here. That's this, valid and data being connected. And then the ready signal going the opposite way is the receive side's input ready being driven by the transmit side's output ready signal. So we can now operate on individual bytes as they go by, and so you can write some code that looks like this, where you at the top here is the loopback as we had on the last slide, but in the lower half we're going to do a fun little demo here where we're going to invert the capitalization of what's going by in the loopback and what's being echoed to the terminal. So we start off, what's the input character? Once it's the data part of the receive stream. The output character is going to start off as being the input character, and then we calculate this little difference between lowercase a and capital A, and we're going to use that to, if the input character is lowercase between the start of the alphabet and the end of the alphabet here, we'll use the case difference to do some math and invert the case of the character. Similarly, if it's already uppercase, we do the other inverted part of the math, and that will change from uppercase to lowercase. Finally, this character that we want to output is actually the data part of the transmit MAC input stream. And if you look on the left here, now when you fire up your terminal and you start typing into it, you should see what you typed return to you, but inverted in case. The last example that we're going to talk about here is using a VGA PMOD, as shown in the top right there. And it's going to be condensed, so we're throwing, here we go, everything for the top level I/O all in one slide here. Your PCF file with all your pins, how those pins map to the PMOD, and how those are which VGA signals. Your top level wrapper, which has your PLL that you now instantiated. Command line to make that PLL. We're taking input 12 megahertz clock that's provided to us by default, and we're outputting the rate for the VGA pixel clock, and eventually you're going to see code that is just driving these simple global variables here, the horizontal sync, the vertical sync, and then the color of the pixel output. I'm not going to go through the entirety of how VGA timing and how chasing the beam works. There are some excellent online tutorials like Project F. But what you will see here is the timing for VGA, the actually walking the pixels across each line is in a header called VGA timing, and if you tell it the size of the screen, it will give you this function here where it is outputting what pixel, the values of the vertical sync and H sync, and if it's in this active area. And so each cycle this ticks along, and every clock cycle is 1 pixel. So what can you do with something like that? You write a little function like this. It's got 2 modules here, the timing, that's producing that signal of walking the pixels across the screen, and then you can take that and put it through some test pattern that says, what's the color of the pixel at that spot on the screen, and you output that color and the rest of the VGA signals. Diving into what is in that test pattern there, the function signature looks like this, right? It's taking the VGA signals as input, and then the output, it's passing those VGA signals through and giving you a pixel of a color at that point. So the copy of the test pattern that's included in this demo was copied from Digilent. It has a box moving around and some color bars, so that looks like a function state machine to keep the box state and move it around over time, and then you go through some function that says give me the pixel color at a certain position, and you can check like if the box is in a certain position, then the pixel color at that spot is the color of the box, great things like that, and you connect your pixel color and VGA signals output. What's great here is this get pixel color is a pure function. It doesn't have any state inside of it, and so PipelineC can auto pipeline that. And in the top right here, an advanced sample of that is sphere versus shapes, which you can find at the PipelineC graphics repo there. And that is essentially replacing, a moving box with a moving sphere. And instead of a simple color, we do ray tracing math based on the position of the screen. And if you're inside the sphere, reflect off the sphere and have this color and bounce off the floor. It's really an impressive project, and I encourage you to check it out. That does bring us to the end here. Again, everything is inside of this dev board setup link. Go there, you'll find links to everything else you've seen today, and ways to ask questions if you have them. Please reach out. Happy to help you on any dev board you have, and hopefully make hardware description easier for you. Thanks for your time. Take care.